Welcome back to the deep dive. Today is February 18th, 2026.
It is.
And look, usually we start these conversations by telling you to, grab a coffee, sit back, maybe go for a run, and just listen in.
Right, the usual podcast routine.
But today is different. I'm actually going to ask you to do the opposite. Put the coffee down.
Or at least keep it away from the keyboard.
Exactly. Pick up a notepad or, open a fresh document on your tablet. Because what we're doing today isn't just another episode.
No. Think of this as a high-level strategic briefing.
That's the perfect way to frame it. So the premise for today is, it's a bit of a departure for us. We want you, our listener, to step into a very specific role.
A very specific and very high-pressure pair of shoes.
Right. So imagine this. You are a senior technical strategy consultant, and you're not just anywhere. You're at one of the top-tier global automotive engineering firms.
The kind of firm that gets the panic call from a major OEM when they realize their 5-year plan went obsolete about, 3 years ago.
Exactly. And you've just been handed a mandate from the board. And this mandate is, well, it's terrifyingly specific.
It is. Your mission is to deliver a top-down and MEC strategic report.
Okay, let's break that down for a second. MEC.
Right. For anyone who hasn't spent a few sleepless nights at McKinsey or BCG, that's mutually exclusive, collectively exhaustive.
Which means?
It means no overlaps in your logic and absolutely no gaps. You need to deliver a complete, watertight, logical framework for the future.
A complete picture. And the audience for this report is key. This is not for the general public. We are not explaining what a V8 engine is.
No, absolutely not. The target here is elite automotive engineers. We're talking chief engineers, CTOs, VPs of R&D.
The people who are way, way past the basics, they're the ones deep in the trenches right now, trying to figure out how to navigate the next, 3 to 5 years?
Exactly. They are the ones staring at their development roadmaps here in early 2026, and they have this sinking feeling that the ground has completely shifted beneath their feet.
So they need actionable intelligence. High level, but something they can actually use.
That's the mission.
Okay, so let's set the stage. It is early 2026. What's the headline of this report we're writing together? If you had to boil down the state of the industry into one single phrase, what would it be?
The headline is that we have hit the strategic singularity.
The strategic singularity, that's a strong statement.
It is. But if you look at the trajectory from, say, 2024 to where we are right now, the industry has gone through a fundamental phase change. It's not just an evolution anymore.
What do you mean by that?
Well, we spent the last decade, maybe more, talking about software-defined vehicles, SDV. We've even done deep dives on that topic.
We have. It was the future.
It was the future. But now, it's officially the old paradigm. We are moving out of the SDV era and into the era of AI-native architecture.
AI native. Okay, I can already hear the eyes rolling in some engineering departments. That sounds like a buzzword.
Agency.
Oh, great, another marketing term from the consultants?
I get it, I do. But it is absolutely not a buzzword. It's a deep, fundamental shift in engineering philosophy.
How so? Break it down.
Okay. For 100 years, automotive engineering was deterministic. It was rule-based.
If X happens, then Y must happen.
Precisely. You write the code, you write the rule, you can trace the logic line by line from sensor to actuator.
If the temperature sensor crosses a certain threshold, turn on the fan. Simple. Traceable.
It's comforting, it's auditable, it's what we know. But AI-native architecture is built on something totally different, probabilistic inference.
So it's not about rules anymore.
It's about likelihoods. It's about learned patterns from massive, and I mean massive, data sets. We are moving from a world where engineers write the rules to a world where engineers curate the data that teaches the machine to write its own rules.
Wow. So the engineer's role is changing from author to, what, a teacher?
A gardener, a trainer, and a guardian.
Yeah.
And that creates the core tension. This is the mission of our entire deep dive today.
Okay, lay it out for us. What's the mission?
We have to reconcile two completely opposing forces in this report. On the one hand, you have what's called the scaling law.
The scaling law.
This is the drive for performance. It's the idea that if you feed the model more data, give it more compute power, it gets exponentially better at driving. This is the gas pedal.
This is what we see from companies like Tesla, Waymo, Huawei.
Yes, they are all pushing this scaling law to its absolute limit. More data, more power, better performance. That's one force.
And the other force.
On the other hand, you have the new safety Bible. It's called ISOPUS 8800.
Okay.
And this standard is trying to wrap a safety cage around that probabilistic monster we just created. It's all about strict containment, safety assurance, verification. This is the break.
So the scaling law versus ISO 8800, the gas versus the brake, innovation versus verification.
That's the entire game right now.
And our job today as consultants is to figure out how to press both at the same time. How to drive the car without stalling it or crashing it. Okay. Let's get into the first section of this report then, the macro view. Because before we dive into the code and the architecture, we have to understand the battlefield. So what's the landscape look like right now in terms of hard numbers?
The numbers are, well, they're staggering. We're looking at market data that projects the global automotive AI market to break $21 billion this year, in 2026.
21 billion, that's a big number.
It is, but the absolute number isn't really the thing that keeps CTOs up at night. It's the growth curve. It's the trajectory.
Right, it's the rate of change. So we're looking at a CGGR, a compound annual growth rate of what?
That's up to 30.6%.
30% year over year.
Which means by 2030, we're aiming for a market size of around $67 billion.
That is just massive growth. But where is that money coming from? Is this new money flowing into the industry, or is it a reallocation? The auto industry isn't exactly known for having infinite cash lying around.
That is the critical insight for our consultant listener. It's not new money. It's bleeding out of traditional budgets. If you look at capital expenditure, at CapEx, the money is literally being siphoned away from traditional mechanical engineering.
So less money for perfecting the piston or redesigning a suspension linkage.
Way less. That capital is now pouring into what we're calling EFLOPS level cloud computing centers.
Okay, let's pause on that term. EFLOP, that's exaflop-es. We throw these acronyms around, but let's just ground this for a second. An exaflop is a quintillion.
A quintillion floating point operations per second, yes.
A billion.
It's a number that's hard to get your head around.
And why on earth does a car company need that kind of compute power? I mean, I thought they needed a wind tunnel and a test track, not a supercomputer that rivals a national lab.
Because the car company of 2026 is basically a supercomputer company that just happens to sell rolling hardware on the side.
That's a heck of a statement.
But it's true. We're seeing companies like Huawei Cloud setting up 5E FLOPS intelligence centers. Tesla's Dojo project is aiming for similar scales. This is a level of compute that, just a few years ago, was purely the domain of national security or fundamental physics research.
And they're building this just to, train a car to understand a left turn at a busy intersection.
That's exactly it. To process the petabytes of data required to teach an AI the nuances of that single left turn.
So if I'm a traditional OEM and I'm used to my CapEx budget going to tooling, stamping dies, casting molds, now my CFO is looking at a bill for thousands and thousands of NVIDIA H100s or B200s.
And the electricity bill to run them and cool them? It's a complete inversion of the traditional cost structure of a car company.
And this shift implies more than just a budget change, right? It must be a cultural revolution.
It has to be. You're pivoting your entire company from a culture of metal bending to a culture of data processing. And this whole resource shift is being driven by one thing: a crisis in development velocity.
The Red Queen race, I've heard this phrase.
It's the perfect analogy. From Alice in Wonderland, you have to run as fast as you can just to stay in the same place.
So what does that look like in automotive terms?
Think about the timeline. Just 3 or 4 years ago, a typical vehicle development cycle. What was it, 24 months?
Maybe 36 if it was a totally new platform.
Right. Today, that has been compressed down to 12 months.
12 months. From concept to validation for a new car, that seems physically impossible if you're still doing things the old way, with clay models and physical prototypes.
For the software stack that defines the car's personality and capability, yes. The hardware might trail a little, but the intelligence, the soul of the car, is iterating constantly on a yearly cycle.
And here's the kicker, right? You have this pressure for extreme speed.
While simultaneously meeting extreme compliance.
Because the regulatory landscape isn't getting any simpler, it's getting more complex by the day.
Far from it. We have the EU AI Act coming fully online. We have this ISOPIS 8800 standard we mentioned, which is a beast. So the engineers are being pulled in two directions. The message from the C-suite is, go twice as fast, but also make it 10 times safer. And by the way, document every single step or you won't be able to sell it.
That sounds like an impossible equation. It's a recipe for burnout or just failure?
It is, if you don't change your fundamental approach.
So, as the consultant in the room, what's the takeaway? I'm advising a CTO who is staring at this impossible problem. What do I tell them?
You tell them that their job description has fundamentally changed. The goal is no longer just implementing functions.
What do you mean by that? Like making the lane keep assist work or getting the adaptive cruise control to feel smooth?
Exactly. That's the old job. The new prime directive, is governing compute and data.
Governing compute and data.
Yes. If you cannot strategically manage the data pipeline that feeds your AI, and if you cannot manage the massive compute clusters that are training it, you lose. It's that simple. You're out of the game.
You can't just buy this off the shelf from a supplier anymore.
Not at the highest levels. You have to integrate this capability into the very DNA of your company.
Okay, let's drill down then. We've set the macro stage. The money is moving, the timelines are shrinking, the compute is exploding. Let's look at the machine itself. Section 2 of our report, the architecture deep dive. You said we're moving into an AI native world. What does that actually look like under the hood?
It looks like the death of the modular pipeline
Okay.
and the rise of the end-to-end neural network, or E2E.
Let's unpack that, because for decades, really, robotics and autonomous driving have been built on that modular pipeline. You have perception, then localization, prediction, planning, control.
Little boxes connected by arrows on a whiteboard.
Yep.
It's a very logical, very human way to organize a complex problem.
Right. Box A is perception. It sees a red light. It tells box B, hey, there's a red light. Box B is the planner. It tells box C, we should probably stop. And box C tells the brakes to fire.
It makes sense. It's debuggable. You can test each box in isolation.
So why are we killing it? If it works, why throw it out?
The fundamental problem with the modular approach is information loss.
Information loss.
Yes. Every time you pass data from one of those boxes to the next, you have to simplify it. You have to abstract it. You have humans, actual engineers, writing rules to translate the rich, chaotic reality of a 4K video feed into a simplified list of objects with velocity vectors.
So by the time the raw data gets all the way down to the planning box at the end, it's lost all the nuance, all the subtlety of the real world.
Exactly. We call it the human bottleneck. The planner at the end doesn't see the hesitation in a pedestrian step, or the way a cyclist is glancing over their shoulder. It just sees a bounding box labeled pedestrian with a position and a velocity. It loses all the critical, subtle cues about intent.
And the E2E approach, the end-to-end approach, it gets rid of the boxes.
It completely blows them up. You feed raw sensor data, video, radar, maybe LiDAR into one side of a massive neural network.
The raw pixels.
The raw pixels. And out the other side come driving commands.
Yeah.
Steering angle, brake pressure, acceleration. That's it.
And the companies leading this are?
Tesla, with their FSD version 12, is probably the most famous example. But you also have Huawei with ADS 3.0 in China. They are all in on this E2E approach.
So how does it learn? If there are no rules written by engineers, how does it know what to do?
It learns by watching. It learns by imitation. You feed it millions or even billions of miles of video of good human driving, and it learns the patterns.
So it's not following a rule that says, if light is red, then stop.
No. It's learning that when the pixel patterns on the screen look like this, a particular configuration of red photons at the top of a pole at an intersection, the correct output action is like that applying brake pressure. It doesn't necessarily know it's a red light in the human sense. It just knows the correct pattern to match.
It's almost like muscle memory or intuition.
That's a great analogy. It's learning the intuition of driving.
This brings us to a really huge shift in how the car even sees the world. And I love this distinction in the report between semantic classification and occupancy networks. This feels like one of those technical details that actually changes everything. Can you explain that?
Oh, this is one of those aha moments for the whole industry. It's a total paradigm shift.
Okay.
So in the old world, the semantic classification world, which is tied to that modular approach, the car's perception system had to ask, what is this object?
It's like a vocabulary test.
Exactly. Is it a dog? Is it a car? Is it a traffic cone? Is it a pedestrian? You have a list of known objects and you try to fit everything you see into one of those buckets.
It's like a toddler learning to name things.
Precisely. But here is the nightmare scenario for every single perception engineer on the planet. The long tail.
The weird stuff.
The infinite list of weird stuff. What happens when the car sees something that isn't in its vocabulary?
Like, I don't know, a sofa that fell off a truck. An overturned boat on the highway.
A strangely shaped rock that just fell off a cliff. Or a person in a weird reflective costume at night that confuses the camera. If the semantic classifier looks at that rock and says, that's not a car, not a person, not a cone, I don't have a label for this, it creates a vacuum. It might default to classifying it as drivable space,
Which means drive right through it.
which is a catastrophic failure.
Mm.
The logic is, I don't know what that is, so it must not be important. That is a fundamentally fatal flaw in the design.
So what's the fix? How do you get around that?
The new paradigm is the occupancy network. Some people call it general obstacle detection, or GOD-ED.
Okay.
And the car stops asking the question, what is this? And it starts asking a much simpler, much more fundamental question. Is this space occupied?
So it's not thinking in labels anymore. It's thinking in, what, 3D pixels? Voxels?
Exactly. Think of the world like the game Minecraft. The car divides the entire 3D space around it into a grid of tiny cubes or voxels. And for each and every one of those voxels, it just makes a binary decision. Is there physical mass here, yes or no?
So it doesn't care if it's a dog, a rock, a bag of cement, or a weird modern art sculpture that fell into the road?
Doesn't matter at all. It just knows that this little cube of space has volume. I cannot drive through it, full stop.
Solid object, do not hit.
It's simple physics. And this approach solves the unknown obstacle problem instantly. Because physics doesn't require a label.
That just feels so much more robust, so much safer intuitively.
It is. But it's not just about seeing what's there right now. The next step is predicting what happens next. And the report talks about world models. This sounds like something straight out of science fiction. It is the absolute cutting edge right now. Think of a world model, something like Drive Dreamer 4D, as the car's imagination.
It's imagination.
Yes. It's not just processing the current video feed. It's building an internal, predictive model of how the world works. It understands spatiotemporal causality.
Okay, that's a $5 phrase. Let's break that down for our listener. Spatiotemporal causality.
It means the car can predict the future based on the laws of physics and an understanding of cause and effect.
How so?
It can run a mental simulation, a what-if scenario. It can think, okay, if I accelerate into this gap right now, that pedestrian on the corner will likely stop because they will see me coming. But that cyclist up ahead is looking down at their phone, so they might not react. They might swerve.
So it's not just predicting where the other objects will go on their current path. It's predicting how the entire environment will react to its own actions.
That's the key. It's a dynamic interplay. It's not just a passive observer. It's an active participant that understands the consequences of its actions before it takes them.
And this has a spillover effect into how we actually engineer the cars too, right? This concept of ACE.
Oh, a huge impact. Computer-aided engineering, CAE, used to be a massive bottleneck in development.
You mean things like running a crash simulation or an aerodynamic simulation on a new body panel?
Exactly. You design a new part, you'd send it to the simulation department, and it would take days on a supercomputer cluster to solve all the complex fluid dynamics or structural mechanics equations.
Days. So you make one small change to a fender and you have to wait 3 days to see if it worked.
Right. It was a very slow, iterative process. Now, with AI-augmented CAE, we can use a neural network that has been trained on thousands of those old simulations to approximate the physics.
And what does that do to the timing?
It reduces the solving time from days to under 1 second.
1 days to under a second.
Yes.
So you can iterate on designs in real time. You could have an engineer changing the shape of a mirror and seeing the drag coefficient update live on their screen.
It goes even further. It allows for generative design. Instead of an engineer drawing a part and then testing it, you can just give the AI the constraints. I need a suspension bracket that fits in this space and holds this much weight. And the AI will generate thousands of possible designs, test them all in seconds, and present you with the most optimal one. It's a total game changer for development speed.
Okay, so we've built this car that learns like a human, sees the world like Minecraft, and can literally imagine the future. It sounds incredible, but here comes the reality check. The safety blanket.
Or the wet blanket, depending on your point of view.
Section 3 of our report. The new safety Bible, ISOPUS 8800.
This is where the rubber meets the road, quite literally.
So why do we need a whole new standard? We already had standards. We had ISO 26262 for functional safety. We had SOTIF, which is ISO 21448. Weren't those enough to cover safety?
They weren't. Not for this new world. See, ISO 26262 is fantastic at preventing things from breaking.
What do you mean by that?
It's designed to handle random hardware failures. If your processing chip overheats and fries, or if your code have a classic bug like a divide by zero error or a wire shorts out, 26262 has process in place to catch that and put the system into a safe state.
So it's about hardware and software integrity.
Exactly. But with AI, you can have absolutely perfect hardware. Your chips can be running cool, your code can be mathematically perfect, no bugs, and the car can still drive straight into a wall.
Because the model itself, the AI's brain, made a bad decision.
Precisely. The classic example is the AI thinking the side of a white truck against a bright sky is just a cloud. That's not a bug in the code in the traditional sense. It's a flaw in the AI's learning. It's a knowledge gap.
And that's the new enemy. The report calls it functional insufficiency.
That's the term. The hardware didn't break, the code didn't bug out, but the model simply wasn't smart enough or generalized enough to handle that specific real-world situation. SOTIF OD800 is the first standard designed specifically to try and wrap its arms around that massive, fuzzy problem.
And the core concept it introduces to do that is this data V model. The idea that in AI, data is the new code. So we have to treat our data with the same rigor we use to treat our C++ source code.
You've got it.
Yeah.
The old V model was for software. This is for data. You can't just have a big, messy bucket of GPGs on a shared drive anymore.
So our report breaks this down, using the MECE principle, into 5 critical data sets. Let's walk through them. Number 1.
First, you have your training set. This is the bulk of your data. And the key here is ODD diversity. It has to cover every possible condition in your operational design domain.
So every weather condition, every lighting condition, every type of road, every type of traffic.
Everything you claim the car can handle, you must have representative data for it in your training set.
Okay. Number 2 is the validation set.
Right. This is what you use for tuning the model's hyperparameters during the training process. Think of it like the quizzes you give a student during a semester to see if they're learning correctly.
And then number 3 is the test set. And this one is, I think, the most critical and maybe the most controversial.
It is absolutely critical. The test set must remain blind.
Meaning
The engineers who are training the model are forbidden from ever looking at this data, ever. If they see it, even subconsciously, they will start to train the model to pass the test, not to be generally intelligent.
Right, the classic teaching to the test problem from schools.
It's exactly that. And this test set has to include adversarial samples.
So you're actively trying to trick your own AI.
You have to. You put subtle, almost invisible patterns on a stop sign.
Yeah.
You project weird images onto the road.
Yeah.
You shine a laser into the camera. You have to find the breaking points in a controlled environment. If you don't know how to break it, you don't really know how strong it is.
Okay, that makes sense. Then we have the last 2.
Number 4 is the production set, which is just the live data flowing from all the cars on the road. And number 5, which is crucial, is field monitoring. This is the feedback loop.
The DevSafeOps loop.
Exactly. When a car out in the wild sees something strange or has a disengagement, that data can't just disappear. It has to be automatically tagged and sent back to headquarters to become part of the next training set, so the entire fleet learns from that one car's experience.
This whole process creates a new engineering challenge called data lineage. The report uses this phrase that I find both brilliant and terrifying. Changing anything changes everything.
It violates every principle of traditional modular engineering.
Explain that. As a traditional engineer, if I'm working on the braking system and I change the compound of the brake pads, I don't have to go back and retest the air conditioning system. The systems are decoupled, they're independent.
Right.
But you're saying in an end-to-end neural network, that's not true anymore.
Not at all. Because the data is the code. The entire system is one interconnected web of billions of parameters or weights.
So give me an example.
Okay. Imagine you have a model trained on 10 million miles of driving data. Your testing shows it's a little weak when it comes to navigating roundabouts in the rain.
A very specific edge case.
Right. So you go out, you collect 500 hours of new footage of just rainy roundabouts, you add it to your training set, you retrain the model, and voila. The roundabout performance score goes way up. Success.
Great. Ship the update.
But here's the terrifying part. When the network adjusted all those billions of weights to get better at understanding rain on asphalt, it might have inadvertently and silently degraded its performance somewhere else. Maybe it slightly lowered the activation threshold for identifying large white objects against a bright background. And now suddenly, in bright sunlight, it's more likely to confuse that white truck for a cloud again.
And you would have no idea that happened until it's too late.
Unless you have impeccable data lineage and a massive automated regression testing suite. This is why ISOPUS 8800 is so focused on this data V model. You can't just patch an AI. When you add that new roundabout data, you have to treat it as a full-blown new version of the source code.
Which means you have to run the entire regression test suite again.
Millions and millions of simulation miles, retesting every scenario you've ever thought of, just to prove that while you were busy fixing the rainy roundabout problem, you didn't accidentally reintroduce the white truck problem.
So for our listener, that chief engineer, the cost and complexity of an over-the-air update just skyrocketed.
Massively. You aren't just flashing a few lines of new code. You are relitigating the entire safety case for the vehicle from the ground up with every single update.
So we're moving, as the report says, from a world of passing tests to a world of arguing safety.
It's an excellent summary. You have to build a comprehensive argument backed by data, by KPIs like robustness, generalization, and explainability to convince a regulator that your black box is safe enough to be on the road. It's much more like a court case than a simple engineering checklist.
Okay, let's zoom out again. This is getting intense. We've built this incredible, powerful, but also very scary AI machine. Now we have to actually sell it around the world. Section 4 of our report covers the geopolitical compliance matrix. And looking at the map you've laid out here, the world is looking pretty fragmented.
It's the balkanization of automotive technology. It's a huge headache for global OEMs, the old dream of the world car. One single platform you can sell everywhere with just a few minor tweaks. That dream is dead.
So as a global strategy consultant, I need to have a different strategy for each major region. Let's do a quick tour of the world. Where do we start?
Let's start with Europe. Europe's role is the regulator.
The rule maker.
The rule maker. If you want to sell a car with advanced AI features in the EU, the EU AI Act and ISOPUS 8800 are your non-negotiable entry tickets. They classify autonomous driving components as high risk.
Which carries a lot of baggage.
A ton of baggage. It means massive documentation requirements, demands for transparency, and mandatory third-party auditing. You can't just push a beta software update to customer cars in Germany like you might be able to in other parts of the world.
So it's a very cautious, permission-first culture.
Correct. Now, contrast that with China.
The biggest single market in the world.
By far. China's role is the data sovereign.
The data sovereign. What does that mean in practice?
It means the core constraint, the number one rule you have to follow is data doesn't leave, model doesn't leave.
So if I'm a German or American automaker, I can't take the video data collected from my cars driving in Shanghai and send it back to my cloud servers in Munich or Detroit to train my global model.
Absolutely not. It's forbidden. New regulations like GB 44495 and the new MIT guidelines for 2026 effectively force you to build a completely separate local walled garden for your AI development inside China.
So you need Chinese data centers staffed by Chinese engineers, training Chinese models on Chinese road data for the Chinese market.
Correct. You are effectively building a second brain for your fleet that is completely isolated from your global one.
That just destroys the economy of scale that the whole scaling law is built on.
It completely undermines it. And it means you might need a third brain, too, because then you have North America.
Then North America's role is?
The decoupler.
The decoupler, okay.
The focus here is on compute supremacy, think NVIDIA Thor chips, and what you could call software sovereignty.
What's the biggest example of this?
The ban on Chinese-developed software in connected vehicles, which is effectively kicking in right now in March 2026.
So this is happening as we speak.
It is, and it's causing chaos in the supply chain. Any automaker, Western or otherwise, who is using Chinese-sourced components LiDAR modules with embedded software infotainment stacks, telematics units, they are all scrambling to rip and replace those components for any car sold in North America.
So it's forcing a hard split in the supply chain, a bifurcation.
A total bifurcation. You're going to see cars that have a Western stack, probably running on NVIDIA hardware, and an Eastern stack, likely running on Huawei or similar hardware. Same car model, two different electronic architectures.
Incredible. So the consultant's advice here is clear. You cannot have a centralized global strategy anymore. You have to have a federated regional architecture for your AI, for your data, and even for your hardware.
It's the only way to survive.
Okay, let's move from the global view to inside the car itself. Section 5, the cognitive cockpit. We're not just driving the car anymore, we're talking to it. And maybe more creepily, the car is watching us.
We are moving so far beyond simple voice commands like, hey car, turn on the radio. We are entering the era of intent prediction.
And this is being driven by large language models, right? The
Ah.
same tech behind ChatGPT.
Exactly. The car is using customized LLMs, things like DeepSeek or variants of Llama, to understand not just what you say, but what you mean, what you
Yeah.
intend to do.
And it's not just listening, it's
Ah.
what's the term? Multimodal fusion.
Right. It's combining the input from multiple sensors. It has a microphone array listening to your voice, but it also has a 3D camera in the cabin watching your gaze, your posture, even your gestures.
So give me an example.
Okay. The system sees your gaze is lingering on a particular restaurant as you drive past. It hears you let out a little sigh, it checks the car's clock and knows it's 12:30 p.m. It puts all that together and proactively suggests, that's a popular Italian place. Do you want me to find parking so you can stop for lunch?
Without me ever saying a word about being hungry.
That's the goal, to be a proactive partner, not just a reactive servant.
But, and this is a big but, with LLMs comes the giant, flashing red warning sign of hallucination. We've all seen chatbots just confidently make stuff up.
And in a casual web search that's funny or annoying, in a moving vehicle, it is a critical safety risk.
Give me the nightmare scenario.
A driver is concerned and asks, "Hey car, is my oil pressure okay?" The LLM, which is designed to be helpful and conversational, might hallucinate an answer and say, "Yes, of course. All systems are normal and running perfectly," when in reality, the oil pressure sensor is screaming a critical low-pressure warning.
You cannot have the car lying to the driver about a critical safety system. That is a fleet-wide recall and a massive lawsuit waiting to happen.
Never. Absolutely never. So the report highlights the specific engineering fixes for this. You don't just let the LLM talk to the driver unchecked.
You put a guardrail in place.
Multiple guardrails. We're seeing architectures like Self-Check GPT or BetterCheck. These are secondary AI systems that fact-check the primary LLM's answer before it's spoken.
How does that work in practice?
Before the synthesized voice speaks the answer, that secondary system does a quick check. It says, okay, the LLM wants to tell the driver oil is fine. Let me check the actual CAN bus data from the oil pressure sensor. The sensor says critical low, mismatch detected. Block the LLM's response.
It's an internal fact-checker loop that runs in milliseconds.
Precisely. And you have a hard physical firewall as well.
Yeah.
We call it the rule-based gatekeeper.
And its job is?
Its job is to ensure an LLM can never, ever have direct physical control over the car's actuators.
So you don't want the AI to misunderstand a joke about it being hot and decide to open all the windows in the sunroof while you're going through a car wash.
The classic open the pod bay doors HAL scenario. You prevent it with a simple, dumb, deterministic piece of code. The LLM can request to open the sunroof, but that request goes to the gatekeeper, which does a simple check. Is the rain sensor active? Yes. Is the vehicle speed over 5 miles per hour? Yes. Request denied.
Simple, robust, and safe.
It has to be.
Okay, we are coming to the home stretch, the final section of our strategic report, Section 6. The Strategic Implementation Guide. This is the so what section.
Yeah.
If I'm that chief engineer listening, how do I actually build this thing? What is the real-world architecture that lets me balance this brilliant, godlike, but occasionally hallucinatory AI with the strict, unforgiving demands of ISO safety?
This is the million-dollar question. And the industry is rapidly converging on a single answer. The doer-checker architecture.
Doer-checker. Okay, break that down for me.
It's a strategy known as acyl decomposition. You split the problem into two distinct parts. You have the doer.
And the doer is the AI.
The doer is the AI. It's your big, powerful, end-to-end neural network. It's handling the complex tasks of perception and planning. It's high performance, it's brilliant, and on a good day, it can drive better and smoother than any human. But, as we've discussed, it's a probabilistic black box. We can't fully prove its correctness, so we accept that. And we only certify it to a lower safety level, something like QM for quality management, or maybe ASIL A. We formally accept the risk that it might hallucinate or make a mistake.
That sounds incredibly dangerous. We accept that our AI driver might make a mistake.
It would be. It would be totally unacceptable, if not for the second half of the architecture. The checker.
The checker.
The checker is a completely separate system running on a separate chip, maybe even written by a separate team. It is not AI. It is simple, deterministic, rigorously tested, physics-based code. And it is certified to the absolute highest safety level, ASIL-D.
And what is its job?
Its only job is envelope protection.
Like the flight control system on a modern fighter jet. It stops the pilot from doing something that would rip the wings off.
It's the exact same principle. The checker constantly monitors the trajectory that the AI doer wants to take. It does simple, high-speed physics calculations. If we follow this path, Will we exceed the friction limits of the tires? Will our trajectory intersect with that solid object that the LiDAR is screaming about?
And if the answer is yes,
If the checker determines the doer's plan violates the laws of physics or a fundamental safety rule, it vetoes the AI. It takes command and engages a minimal risk condition.
it slams on the brakes or steers the car safely to the shoulder.
Exactly. The AI is the creative, brilliant genius driver. And the checker is the strict, boring parent holding the safety leash, ready to yank it back at the first sign of trouble.
That makes so much sense. You can't prove the genius is perfect, but you can prove that the safety net will always catch it.
It's the only way these systems are getting certified for production right now.
And to build all this, we need new tools. The report wraps up by mentioning OpenUSD and agentic AI.
Right. Tooling is everything. OpenUSD is quickly becoming the lingua franca for digital twins. It's the common file format that allows your complex simulation data to move seamlessly between different tools, from NVIDIA's Omniverse to ANSYS simulators. It's all about interoperability in the toolchain.
And agentic AI.
That's about surviving the Red Queen's race. It's about efficiency. We are now using AI agents to automate huge chunks of the development process, using an AI to write the millions of test cases you need, using an AI to generate the simple deterministic code for the checker, using an AI to run the simulations and analyze the results. The goal is to automate 30 to 50% of the entire V model.
Because human engineers just can't type fast enough to keep up anymore.
They can't. If you try to do all of this manually, with human engineers writing every line of code in every test case, you will fail. You'll be too slow and you'll miss something.
So we've reached the end of the briefing. We've gone from the $21 billion market shift all the way down to the nitty-gritty of a doer-checker architecture. If you had to provide the final synthesis for our listener, for that chief engineer, what is it?
The synthesis is that their identity has to change. If you are an automotive engineer in 2026, you are no longer a builder of functions. You are a trainer and guardian of AI.
Your value isn't in writing the perfect C++ code that controls a fuel injector anymore.
No, your value is in designing the data sets that teach the AI how to drive, and in architecting the safety cages, like the checker, that keep that powerful AI in check.
It all comes back to that core tension we started with. Innovation versus trust. The scaling laws versus ISOPUS 8800.
And that leads us to the final provocative thought we want to leave you with.
Here it is, the big question.
In this new world of end-to-end black box AI, we are moving to a place where safety is a statistical argument, not a mathematical proof. We can prove mathematically that the checker works, but we can never fully prove or explain why the doer made one specific decision over another.
It's a leap of faith, backed by a mountain of data.
It is. So the question for you, as you're the one signing off on these system architectures, is this. When your AI driver makes a life or death decision to swerve or to brake, based on a probability distribution inside a black box that you, the engineer, cannot fully explain, are your assurance cases strong enough to defend that decision in a court of law?
Wow.
Because eventually something will go wrong. And a lawyer in a deposition is going to look you in the eye and ask, why did the car do that? And the answer, because the neural network's weights converged on that solution, is just not going to be good enough.
That is a chilling thought. It's the midnight anxiety for every engineer in this field, but I suppose that's the reality of living through the strategic singularity. You have the map, now you have to drive the path.
Good luck with that report.
Thanks for joining us on this deep dive, and drive safe.